of you talk? Please raise your hands. 1, 2. Okay, not bad. You two will hear some things twice. So, but hopefully there are newer things here. So I'm going to tell you the kind of the overall story of Charm++ and some of the concepts. So is Charm++ a system that, where's the echo coming from? This one's off. Okay. So it's just, I think it's just a loop. Yeah. Okay. We just started developing Charm++ a long time ago. It's a project that's been running for a long time. I don't know if it's an embarrassing thing or a good thing, but we have been developing Charm++ for 15 plus years now. It's a very mature system now. It's a parallel programming system. It's based on C++. Many of you are coming from the vendor side, so you need to know it's not some weird academic language. It's C++ with a little additional processing for allowing remote serialization of data and so on. And it's in production used on many full-fledged parallel applications, as we'll see. So what I'm going to do in the talk is give you some basic ideas, and some of those basic ideas are now becoming pretty big in high-performance computing. So you will see them arise in other programming models as well over the next few years. And then give you some application examples of what kind of applications we do with it and what advantages it brings to those applications. And then talk about some of the features back again and some advanced features like fault tolerance and so on, and conclude with some additional data. So this is of course a fairly large group that helps me with this. This is a picture from last year's workshop. We have an annual workshop on Charm++. This is a 10th annual workshop picture. And we work with many collaborators, including rocket scientists that you heard from, not that rocket scientists, but rocket scientists as well as molecular biophysicists and so on. So you will hear about several of these collaborations as well. So if you think about computer scientists working on parallel programming, not counting the numerical analysts, then usually you get the people doing parallelizing compilers, right? And the idea of parallelizing compilers was basically that there is some magic happening somewhere in the system. Automatically parallelize a given sequential program. It was a very nice vision. Even now, when people think about multi-cores and so on, the view typically is, oh, we have a compiler flag we can use, and it's never been that easy. Compilers have never been able to automatically parallelize programs because sequential specification just hides and obscures too much of the parallelism in there. Instead, what we seek is an optimal division of labor between the programmer and the system. So programmers are smart people. They can do their part in identifying what to do in parallel. The question is, how can we leverage the system the most so that we reduce their burden the most? And the second thing that we decided to do right from the beginning is to design our abstractions based on use cases, not based on just one application, and not just based on platonic idea about what's a beautiful computer science concept either, which is very prevalent in computer science. So the idea that there's only one central idea that everything else derives from. That idea is object-based over-decomposition. So let me take a minute to explain that idea. The basic concept is very simple. Normally, when you write an API, when you write an API program, you divide your computation, you divide your data. So the decomposition is a natural part of what you do as a programmer. Well, we just ask that you over-decompose. When you over-decompose into large number of pieces, so you make the number of pieces, and those pieces can be work units or data units. So as an abbreviation, I call them groups, work unit data units pieces. Those pieces can be unrelated to the number of processors. So your programming model becomes independent of the number of processors. And then you let an intelligent runtime system assign those pieces to processors. And then that assignment is not static. The runtime system can change it, and this becomes feasible. Oh, I don't know what I'm doing wrong with this guy. I think the pin is on. Thank you. What am I setting up? Okay. So I'm too tired, I guess, here. So let me try not to move much. The idea is that objects, these entities don't talk to processors. Typical MPI programs, you send messages to processors. You don't want to send messages to processors, you send messages to these voodoos. And therefore, if I pick one of them and put it somewhere else, the application doesn't need to know it's talking to that guy. That guy happens to have moved, but it doesn't need to know that it has moved. The runtime system knows it has moved and it delivers to the right place the data that needs to go there. So this empowers the runtime system to do all kinds of interesting things, and that's the agenda. What it can do lots of interesting things, but we need to actually invent and do those things. That's been the runtime agenda that we've been following for the last 50 years. And I didn't imagine it would go this long, but it has been going this long. It has gone and it will keep continuing on as we go to exascale machines and beyond. There will be new research issues, but the conceptual part, the programming related part, the application related part is now mature. So the particular realization of this idea in CharmLU was in terms of C++ objects. So we just said, let's decompose the computation into C++ objects. Let's organize these C++ objects into index collections. So there are multiple collections. Within each collection, all the objects of that collection have an index through which to address it. The index might just be one dimensional. So we might say A sub 23, which means the 23rd object of the collection A. And you want to invoke a method on it is how you communicate with it. But the index might be 3-dimensional, it might be 6-dimensional and sparse, or it might even be some bit vector. So the index structure can be anything that you want. So the programmer then expresses the computation in terms of these objects and interactions between them, and they are not aware of processors. Processor is something that the system worries about, and it maps those objects to processors and can change that mapping as needed. So like I said before, this has been developed in the context of many applications. So some of our well-known applications include AMPI, which is probably the most scalable biophysics simulation code, one of them for sure. And we won the Gordon Bell Award for it in 2002. But we also were involved in the precursor to the PSAP Center that you heard about was something called ASCII, and we're part of the ASCII Center at Illinois doing the rocket simulation, and we applied our ideas there. But our production simulators today available today on carbon machines include NAMI, CharmLU, which is for astronomy, and OpenAtom, which is for nanomaterials, nanotechnology, and quantum chemistry. We have agent-based simulation, we have stochastic optimization code, and several others, and full examples from some of these as we go through. So the runtime system is now empowered. It can migrate these objects around at will. It can schedule them at will on a given processor. Which one to do next is up to it, not up to the program. And so that freedom it can use to do interesting optimizations. And it can instrument, since it's involved in delivering method invocations to objects, and it's involved in scheduling them. We know it can actually keep track of things such as which object is talking to whom, how much long this execution log on this object takes, and it can keep track of the historical data and do interesting things like load balancing based on that. In this era of multi-core processors and very-core processors and so on, another thing that comes handy is the fact that when we decompose the computation in terms of objects very naturally connote locality, and so therefore the program is very naturally locality aware. And so this, the second fact is, since there are many objects on each processor, the execution is naturally message-driven, right? In other words, whom am I going to execute next? What code am I going to do next? Well, there has to be a scheduler. That scheduler will work from a pool of method invocations, which in case of CharmLU will be method invocations. In general, it could be messages of some kind. And you look at the message, the scheduler looks and says, oh, this is meant for this object, invokes a method in that object, lets it do its work, comes back to the scheduler, and then you continue the execution from that point, right? So this means that couple of things. You know ahead of time what object and what code is going to execute next. This is actually a great principle of prediction. The whole entire cache hierarchy that the industry built over the last 40 years was based on this principle of locality heuristic, which is a very approximate heuristic. It doesn't work very well, as you know from our performance experience. Well, this one is almost perfect heuristic because we pick at the code, we pick at the queue, and we look at the code is going to execute and the object is going to execute on, and we can actually use the historical data to see whether it touches all the data of the object or not. So we can actually, we have a perfect opportunity for doing things like prefetches into the scratch pad memories of processors, for example, the cell processor. So a variety of things can be done with like that on these medical processors. Now if we look at communication, the way the communication networks are used in MPI programs, it's typically a bulk synchronous like compute communicate cycle, very commonly, right? And so, so you look at an application and say, well, my application is not performing very well. It's spending 30% of its time in communication. Then you say, well, let me optimize it. And you work on various things like moving the sending of the communication to the left and whatnot. And then you finally say, well, now I got my communication down to only 10%. And you're very happy about the optimization you did, but what you accomplished is that you're keeping your network idle for 90% of the time, right? You're using your network 10% of the time and keeping it idle for 90%. Why are you not worried about utilization of the network? Well, so so what happens as a result, we put pressure on the vendors and say, hey, build us a faster network, cascade, infinite band, new version, and so on. We over-engineer our networks for that reason. If you're doing over-decomposition, the communication naturally spreads over the iteration of the time step, and the latencies are very naturally tolerated. For both of those reasons, you actually are using much better use of the network, and you either can live with a lower capacity network, and actually can go much further with the networks that you're building, and communication becomes less of a problem. I wouldn't belabor the next point that much, but it's a very important point if you're doing a multi. You heard about the rocket simulation here. There are all kinds of projects that involve multidisciplinary collaboration. Many different codes need to come together to work in a single. In our rocket center, we had to do this. I'll show you an example of that in a second. But multiple modules need to come together and work together. You need to be able to do a composition of those modules in parallel. And it's hard. With MPI today, what you can do is you can say, well, modules B and modules B are independent. They can both run. What I'm going to do? Well, I'm going to have half of my processor go to B, half go to C. Or I say, well, that's all. Yes, they can be done in parallel, but let's all do B first and then do C. Right? With message-driven execution, what you can do is you can start both B and C, and then let the execution happen and interleave based on availability of data across processors, right? And this kind of thing allows you to overlap the idle time in one module to useful computation in the other module. And that's true parallel computation. At the rocket center, we had solids and fluids, and I just abstracted out an example from that. We're doing a solid rocket booster of the space shuttle. But that's not important. If you have a solid and fluid, typical MPI doing thing is you partition the solids mesh in 100 pieces, partition the fluids mesh in 100 pieces, and then 17th piece of solid and 17th of the fluid runs on one processor, 17th, because the partition is called them 17th. Okay, no other geometric reason than that. This is a very common state of affairs in this field. Instead, with this CharmLU approach, you just make separate sets of objects for solids, M objects for solids, N for fluids, doesn't matter. And then let the runtime system figure out who talks to whom and accordingly bring them together as the program executes. Now, CharmLU is well and good, but people are used to doing MPI programs. Yes, we can actually, what we did is we developed something called adaptive MPI, where each MPI process is implemented as a user-level migratable thread. For those of you who know something about threads and migration, you know this is a pretty tricky thing to do, but it can be done. And so these threads are embedded inside CharmLU objects, and then the chunk plus runtime system takes over and does the same object assignment. So one success story of that, there is a code called RAMS, and the Brazilian version of that for weather prediction, and the Brazilian version of that is called RAMS. So someone from that group came to us, spent a year with us, and spent some months of that creating this AMPI version of that code. So what happens is you have this is the map of the Brazilian coastline, and the next picture you see a storm passing through. On the right you see a bunch of processors, and you can see the loads on those processors as the storm goes through changes. When there is more moisture, you're doing more work. So if you run this on regular 64 objects and 64 processes of 64 processors, you get a load imbalance. This is the y-axis, is the utilization. So the rest is the idle time, the white space is the idle time, and you get load variation plus a lot of idle time and off. That's coming because of critical paths. By doing over-decomposition, first just by doing over-decomposition, going to 1,000 objects, you get the idle time down because you're overlapping computation and communication, a couple of other factors that I won't get into. And then by adding load balancing, so for this, instead of decomposing to 64 objects, you decompose into 1,000 objects, right? And then running 164 processors, we then apply load balancing, you get actually the load on all processors is pretty balanced as well. As the storm moves through the objects, you go around the system, and you can see that the performance improved from something like 5,000 seconds to 3,300 seconds for this simulation. Our most well-known program source is NAMI. Has 45,000 registered users. It runs on all the computers that we have access to. And basic biomolecular simulation is pretty classical in nature. Quantum effects are just pushed under a rug called force fields. I'm going to run out of power. Maybe we can try to get one extenders from there. I really appreciate that. Have a long. Okay, so and so each time since you're just calculating forces on atoms due to electrostatic forces and bonded forces, and then continuing on to the next, integrating them and continuing on to the next step. The problem is the time step is 1 femtosecond. And we need to be simulating nanoseconds to microseconds. So really, literally millions to billions of time steps are needed. Thank you. And so long time ago, in the mid-90s, when we designed NAMI using Charm itself was being designed at that time, we decided the previous approaches being used at that time were not scalable. And that's because they started from sequential codes and trying to just graph one parallelism onto that. But some people were doing spatial decomposition, limited in particular in that around that. So the first thing we did is spatial decomposition. First, put atoms in their cubes, and then let's do the simulation based on that. Well, that actually creates load imbalance, and the parallelism is limited. But then with Charm++, we were able to do a different scheme whereby what we did is we said for every set of cubes, let's postulate an object. This is a diamond color object there. Whose job is to calculate interaction of forces between them. So now we have two sets of objects. So no problem. We just give them the Charm++ to load balance, right? And so then of course there are other things that you have to do. You have to do particle mesh AWOL, which is involves 3D FFT. For long range forces, you have to do bonded forces. Yeah, but all that does is add a whole bunch of sets of objects, and we just give those objects a right programming terms of those objects and communication between them, and then the runtime system manage the load balancing. This design was done in '95, and we're using that HP cluster, connote HP cluster, and it has survived till today with maybe, of course, refinements, but the basic design is the same. It runs on half a million cores of blue hours. To just show how this overlap works, the blue is the electrostatic force calculation, which is the dominant part. X-axis is time. Y-axis is also time, but it's actually it's a histogram. It's a stacked graph of time spent during one particular time interval added across all processors. And so you can see in some time intervals you're doing more red work, some time intervals you're doing red and blue and so on. Red is the integration, blue is the electrostatics, and some other parts. You can see that overlap between various different components is what gives this gives the AMPI's performance. Open Atom is this collaboration with Glenn, of course, AMPI is a collaboration with Klaus Schulten, and originally Bob Keel, the numerical methods person. This one is a collaboration with Glenn Martina mostly, and it's Carver nano method. And the interesting thing about this is simply, I won't get into the details of that, but we can actually do fairly good strong scaling, taking small molecular systems and running them on a large number of processors. And this, I was talking about the fact that there are 3 or 4 different classes of objects or collections of objects in AMPI. Well, this one has over a dozen different collections of objects. There are objects corresponding to the real space decomposition of the reciprocal space representation of the electronic structure, real space representation, and so on and so forth. There are maybe a dozen different types of objects, and the runtime system can control the mapping and assignment of these objects to processors. Astronomy is another example. This is a collaboration with Tom Twin. And this is simulating evolution of the universe, starting with what we know about the early universe based on the microwave radiation that you see around us. That tells us gives us some idea about what the basic structure of the universe was at that time, distribution of matter was, and then you evolve it through using your knowledge of relativity and gravity and so on. And then you say, well, does it match? I think it's going to talk about the mass. This time for good. It doesn't have it clicked that far. Oh, it's looked down. Oh, I see. Is that the video? I think I hear you. Yeah, and you guys can hear me anyways. Yeah. But I use my phone. Yeah. Okay, I know this is my hand. This is going to be volume. So, alright, so in the meanwhile, you got to stare at this beautiful galaxy picture. But optics is a very natural decomposition for these kind of computations. People don't use optics because they are not load balanced. Why? Optics use optics and give the load balancing to us over decompose, which is the idea behind this code called Changa. And this Changa code has scaled very well as well to a large number of processors. It's one of the codes that SFS selected for running on blue orders, and so is AMPI actually selected for that. A more recent code that we developed is an agent-based simulation of spread of contagion. The contagion can be information, but the contagion can be disease as well. And in this particular case, I think I click it somewhere. Okay, so this is simulating something that began in Seattle in the top left corner there, and that contagion is spreading all over the country. And it's a simulation based on people and places done by Madhav Marathi and Keith Bissett from Virginia. And so it's a very different type of application than our regular science and engineering applications. But it turns out that this performs. They had an API-based code, and then they collaborated with us and we did a CharmLU based version of this code, and the CharmLU based version is performing much better, scaling much better because of the support for asynchrony. CharmLU has asynchronous reductions, and that turns out to be a useful feature here, as well as in AMPI. You know, in molecular dynamics, every time step you need the total energy, but you really are not waiting for that total energy. So why if you use API reduce or something like that, you're not waiting for that application to finish, and you can do without that. So various types of asynchrony is very natural outcome of the message-driven execution that's part of CharmLU. And so they're able to simulate large things like this very effectively using CharmLU. Going to slightly older time, there is a collaboration we did with Philip Gribel that involved structural dynamics. So the experiments that we did were things like crack propagation or elasto-plastic fractures. So what's happening I think in the bottom picture, probably both picture, is that the elements turn plastic as the stresses propagate through the particle. Plastic elements require more computation, which causes load imbalances. And so if you look at this picture, which is from an old version of performance visualization tool called projections that you've been seeing on the previous slide from Andy as well, you see on y-axis utilization. And if you did load balancing at the top, the utilization drops down dramatically at the point that some elements turn plastic. Because some elements turn plastic, they require maybe twice or more the work. Those processors are slowed down. The application is tightly coupled, of course, and so everyone is slowed down. So you don't get this situation in parallel computing. If some processors are slowed down, everyone has to slow down. Unlike math and use, well, I guess you have some of that element in big data spaces as well. But you have a highly tightly coupled, in every time step you must synchronize type of a scenario. And so the load balance is felt very badly in such a situation. So then as the more and more elements turn plastic, things become slightly better balanced, but then it flattens at a bad point. It doesn't flatten at about close to 100%, maybe 60% or 70%, somewhere in between. By using load balancing, every so often, and you see that jitter, that's the load balancer, right? And so every so often on this bottom curve here, which I don't know if you can see, yes, that curve, you can see that jitter there. So every so often it's load balancing, bringing the thing balance back into the rack. It's gone out of the back, it brings it back, and it continues on at pretty high utilization for a relatively short amount of time. So something that took 800 seconds now finishes in 600 seconds. And in fact, it was especially useful when they were trying to do a 24-hour simulation, which were able to finish in 18 hours. That's a significant saving of that. When you go to a large number of processors, the advantage becomes even more. Just pictorially to illustrate over-decomposition, again, a very old picture is, instead of decomposing something in 16 pieces, you decompose into 128 pieces. No big deal, and then give those 128 pieces to the runtime system. So all these applications now are being written up in a book, which should have come out by now. And the chapter authors, if there are any in the audience, please update your chapters. But anyway, that's one of them is me. So in a couple of months, this book should go to the publisher and be read. Now we're going to switch and talk about some nice features in Char. Yesterday you heard from John. I wasn't here for the talk about the importance of power and energy as separate constraints. So we've been working in that space as well. It turns out this same over-decomposition idea is very useful there. Let's just think about, for a moment, about just cooling energy, right? How much energy you spend on cooling the HPC data center, right? You want to save that. Well, saving that cooling energy is very easy, right? You just shut down the AC. Or move the thermostat up. If it is at 14 degrees, change it to 20. If it is 18, change it to 24, something like that, right? Well, there's a problem. There's a reason why it is kept cold, is because some processors are going to overheat and burn out the device, right? And so all right, so then what do you do? Well, these days it's possible to monitor the temperature of each core, each chip, through on-chip sensors. You monitor the temperature, and you say, oh, this chip is getting so hot every so many seconds, let's say every 5 seconds, you just check the temperature, and accordingly, if it's too hot, reduce the frequency. If it has gone cold enough, increase the frequency. Now, that's fine. If you reduce the frequency of one chip out of 10,000, what happens? Everyone else slows down for the same reason as before, right? It's not because there is some elements turning plastic to plastic now, but it is just the processor got slow. So everyone has to become slow because that one guy is slow, right? And so what do? Well, load balance around it. So every time you actually change the frequency, just make sure your load balancer is rate aware. It's aware of the rate at which processing is happening, and then it can balance the load correctly with that. Right? By moving, the fact that you have tens of objects on a processor is key to be able to do this. The load balancer, which has to happen automatically without the programmer intervention, it has to happen inexpensively without having to do repartitioning of the whole data space. And so all of that is possible because there are tens of objects on a processor. You just lift the right number of objects away from that processor, and everything comes back into balance again. So this was written up in our SC11 paper, but there are several new power-related strategies that we've been working on. There are things about power power and energy. Well, power is a limit. That is how much how much power you can burn at a point in time before the fuses blow and the power stops or something like that. Large data centers such as Blue Waters machine and so on take 10 megawatts plus minus power, and so you need to be within your limit or bad things are going to happen. Energy is the bill that you pay at the end of the year, and you want to minimize the energy while staying within the power constraint, and of course execution time is your main constraint. Your jobs need to complete in good time as well. So doing this multi-dimensional optimization is helped by having this ability to move objects around. And so there is one recent paper in a conference called PASA 12, and so that has some more work on it. A lot of our work is available on our website. This thing here just pictorially shows some of the benefits. X-axis is the energy, Y-axis is the execution time, and this was the temperature where load balancing that we did. And the colors are badly chosen. I think the green should have been red should have been green. So the green curve is without load balancing, and you can see what happens, right? That's when you're saying, oh, this chip is too hot, let me reduce its frequency. What happens when your execution time increases? If your execution time increases, you're going to not save any energy, because yes, you reduce the power of that one guy, but your energy became actually more because you're executing for a longer time. And so with load balancing, you can actually, of course, the green curve still make sure that no chips are burning and it's saving cooling energy, but that saving energy and cooling energy by increasing the AC thermostat is lost in the fact that you are running for a longer time. The red curve is for every corresponding point, like the topmost point is 23 degrees Celsius as the thermostat. And you can see that from that, you come from that point here to that point here, and using the energy as well as using the execution time. In other words, not reducing the execution time, but minimizing the penalty that you pay from the execution time. Compared with the 25% here, it is maybe 12% here. So that's one thing. The other thing that is going to happen as you go to the future is faults. If you listen to Shaker Broker from Intel and other people, they're talking about, the fact is that around 2003, the frequency stopped scaling, right? Many of you are young here, but you know, when you may not remember 85-ish time frame onwards, how it has been that every year we go and buy, every couple of years, buy a 33 megahertz processor, and then you get a 66 megahertz one, and so on. We've been doing that for many, many years until 2003 or so, when we hit maybe 3-4 gigahertz, and then we slid down to 2 gigahertz again, right? So frequencies are not going up, processor speeds are not going up, but we're still most likely doing fine because we are still keeping more and more transistors on the chip. So that's okay. But as you go further, the power becomes a important consideration. It cannot be 10 megawatts for a 10 petaflop may be okay, but a gigawatt for an exaflop computer is not going to be okay. And so for obvious reasons. And so we're going to figure out a way of generating more computation for and less hot air. That is for generating more computation for less energy, right? And so how do you do that? Well, so some of the things they are suggesting is things like near threshold voltage computing. So your voltage of the supply voltage of the chip maybe has already come down from 5 volts to 3 volts. You keep bringing down to the threshold, which I think is 0.7 volts, I don't remember what it is. But once you bring it closer, you have to run it at a much lower frequency. Once you run it at a much lower frequency at low voltage, well, at that voltage, the difference between 0 and 1 is small, so you get more errors. Transient errors and faults of all types become more common. How do you live with faults becomes one question, right? And in any case, when you are working with a large number of components, which we often do, but not probably everyone in this room needs to, when you run on a machine with 25,000 nodes, which the Blue Water machine is, or 1.6 million cores, which I forget would be 100,000 nodes for the Sequoia. That's a lot of components, and the failures are going to be common, simply because the probabilities are low, but the number of components is high, so some component will fail. So CharmLU, again, leveraging this technology of objects, has been working on that, has had several features. The blue features there are the production features that have been in our distribution for many years, and the other features, the proactive and message logging, are experimental features. And message logging is now almost on the way of becoming a production feature. I'll tell you a little bit more about those features. In particular, the in-memory double checkpoint. Yesterday you heard from Ankita about the RAM cloud and the idea that you can maybe use the RAM cloud instead of the disk. Well, one idea is you can use the RAM for storing the checkpoints. So instead of the traditional method of checkpointing is you checkpoint data into the file system. And the file system on these supercomputers is notoriously bad. In addition to being inherently slow, it's also non-inherently bad as well. But anyways, it is much better if I can store my checkpoint in this other processor's memory. And if the other processor's memory is not enough, well, store it on flash. That's coming. Some non-volatile memory storage is coming anyways to the supercomputers near you. And so store it in that. And then you need to be a little bit clever about it, because if I store a checkpoint in your machine, if I crash, I can fetch it from you. Everyone needs to fetch their checkpoint though, and so the guy who stored their checkpoint with me, who are they going to get it from? So you have to store it in two places, and one of those two places can be yourself. Right? You store one checkpoint locally, one in remote. If you crash, you get the retrieve your checkpoint from your buddy. Everyone retrieves their checkpoint from their own memory or their flash, and then you continue. This idea has been fully automated in CharmLU. It's not something that the user has to do in their application. It's because for migration purposes, we can pack an object and move it. Whatever technology we need for that, we apply the same technology to checkpoint that object at the checkpoint time. So fully automatically, by specifying one thing on the command line, linking the right version of Charm, and adding a place in your program that says, at this point in every so many iterations, I want to do the checkpoint. You can create these checkpoints, and the system will retrieve from false automatically. For something like NAMD or molecular dynamics, it can be very fast. So, for example, here is data going to 64K for LeadMD, which is a bit smaller version of NAMD. It's just experimental code that does something like basic steps of the molecular dynamics. And storing a 1 million atom system, the checkpoint time is what? The x-axis looks like 4, but that 4 is milliseconds. Okay, so in 4 milliseconds you are done storing your checkpoint. And the recovery is also very fast, although there is a logarithmic component to the recovery cost. From the time that you are notified that one of the node fails to the time that you have brought in a spare, and this works with spare or without a spare, but typically we like to work with a spare node. So you just use one of the spare nodes, retrieve the checkpoint, and continue. Well, that is something like 150 milliseconds in the worst point at the top, 64K processors there. Of course, to detect it, you might need to use some heartbeat, and that might take a few seconds to detect. Once it is detected, though, it takes a really small amount of time. Now, of course, applications that fill in memory, maybe half of the memory in their checkpoint, well, those would not be that quick, but they'll be a second or two. And we have done those experiments as well. I just want to tell you about one other project that we did some time ago, so it need to be dusted off, but it's very relevant today for the cloud. The project was called Faucets, and that's another great faucets. It's just thinking of compute power as a utility. And the idea here was you want to leverage this object ability to migrate objects at their adaptive runtimes for high throughput within a cluster, increase the resource utilization within a cluster, also utilization across clusters. So you submit a job, the job will run on any one of the 20 clusters that can run the job, and there was some idea of a market-based bidding system for that as well. And then there was one component of that project which was also worrying about how to run a single job on multiple clusters, leveraging our latency tolerance capabilities. I will tell you about the first part, resource utilization, just a simple animation showing 16 processor, 16 node cluster, just for an example. Not fun to draw 1,000 word in a picture like this, but it will work the same idea works. So you have a job A that requires maximum 10 nodes. Okay, it cannot run on, cannot utilize more than 10. All right, you give it the 10 node, it starts running on the 10 nodes of your 16 node system. Then a job B comes along and it says, I need at least 8 processors. Maybe it can run more, or maybe it wants at least 8 processors. What would you do? You have to keep that job aside. There are only 6 nodes available to you, and so you just have to keep that job aside until it finishes, right? And so that conflict means that you waste a lot of resources, those 6 nodes sitting there idle. Well, with an adaptive job scheduler, what you can do is it can take advantage of the adaptive. You can say, well, shrink an existing job. You can tell a job basically a bit vector. Say, here is your bit vector of nodes you can use, and you can change that bit vector. Then the load balancer will say, oh, bit vector changed on me, I need to migrate objects around and vacate from these processors and start using these processors. And do that and tell the scheduler, yes, I have complied now with that. So with that kind of thing, what you can do is when job A comes, sure, it will start running on 10. When job B comes and says, I need at least 8 and maybe as many as 16, you say, fine, you get 8. Ask the first job to shrink itself from 10 to 8 nodes. It will do that by using this object migration business. And then you start running B, and when B finishes, well, A can expand to the 10 that it could use maximally anyways. So you could actually increase your utilization significantly by doing this, and this was some work that we did in that time frame that is now becoming more relevant in the cloud context as well. So this is just a picture showing shrink and expand up to a certain number of time steps, 600 time steps, we are running at the speed of, point that y-axis is time per step, at the speed of 140 milliseconds per time step, and then at 600 time steps, some more processes became available. I said, okay, fine, I can use them, and we start running at twice the speed now, right? So this is an actual run on sometime during that time frame, 2004 or so, that we were able to demonstrate in same-time programs. So there is a competition that is run every year at supercomputing called HPC Challenge. Class 1 awards are for machines, so which machine is more powerful, and with some benchmarks. And Class 2 awards are for programming languages, which programming language is productive as well as reasonable performance. And so our submission to this competition started only last year. 2011 was the first time we submitted this competition, and we actually won that award along with Chapel, which proves to me that if you design a parallel programming system, its name must start with CH. That's the only, the other one was for a Fortran. Well, but that hypothesis went wrong this year. We were a finalist this year, but Extend and Chapel won. Given that Extend and Chapel are heavily funded, funded, or at least for a number of years for this productivity program, I'm happy to be in their club as a finalist. But I think we have a much more mature system there. So just to show some results from that, this is CharmLU, which is an implementation of the HPL, the impact benchmark. Something as so diverse set of applications we can do pretty well on, and this is showing 67% of the peak on Jaguar, which is pretty creditable compared with what people do. Given that this is done with just Charm++, not doing any assembly coding, not doing any low-level optimization for that, and so on, it's only 1650 lines of code. So that's one metric that this competition uses for productivity lines of code. This table here is, I'm just going to show it, not dwell on it. I'll just maybe tell about some benchmarks. We have AMU, we have the liquid dynamics benchmark in this year's submission. We also have AMR this year. And AMR is actually pretty interesting. Those of you interested in structured adaptive meshes, please ask me about it afterwards. I'll tell you what we will be able to achieve on that. And we have this fast triangular solver. Last year's submission, in addition, did not have AMR triangular solver, but included Barnes Hut, which is a range of some sort among some subset of people trying to show productivity of their programming models, and we were able to show pretty good performance on the Barnes Hut as well, going to 16K processors for that benchmark. So finally, many of you are from vendors or ISVs. I want to tell you that CharmLU is a production system. It has to be to support our 40,000 plus users. We had yesterday, you heard about all these software practices. We do most of them. We don't do this nice, beautiful picture that is shown yesterday. I'm going to investigate that for sure. We use Git. We have a nightly build on dozens of machines, different supercomputers, different compiler-computer combinations, and regression tests, and so on. And we have a tools ecosystem. You saw some snapshot from projections, and yesterday you heard Saratari talk about, from NVIDIA, talk about how she thinks projections is a much cooler tool than she compared with the industry tools and so on. We are very proud of that tool. We also have a debugging tool called CharmLU. We have an ability to do live visualization of applications, which is typically tricky for most programming systems to do because they talk about out-of-band communication. Out-of-band is no problem for us because it's doing basically a message-driven loop. Whether the message is coming from the application, whether it's coming from the visualization side, every node can, every processor can handle the messages securely. And so we can do live visualization based on that. One final obstacle that we overcome now is that some people say, well, we have a big application and it's all MPI application. We don't want to transition off to, or we don't want to buy into your module, your idea about everything. Well, you can now program most of your application in MPI and do one module in CharmLU. So it supports interoperability. You can do time sharing, whereby you're doing the shared stuff with MPI for a while, then you switch to CharmLU module, then you come back from CharmLU to MPI module. That's one mode. The other mode is space sharing, where some processors do MPIs, some do CharmLU, and they are communicating across. And all of that requires some support that's already built in, and we can combine those two modes. So, during the last year, some of the work that some of you may be interested in includes the ports to various new machines. We run on top of MPI, but we prefer to run on lower levels. And so there is a Eugenie port, which is for crane machines, and Hamid port, which is for Eugenie machines. We have load balancing decisions. Usually, in earlier times, you still have to say, do load balancing every 20 steps. And we're trying to automate that. When to do load balancing, which strategy to use for load balancing, the AMR that I mentioned earlier, and so on. And there is some work on cloud. There is support from HP for part of that work on the cloud that's going on as well. So to summarize then, we have, if you look at everything that I told you so far and try to line it up, we say initially you have over-decomposition. Actually, message-driven execution very naturally follows from that, but over-decomposition is not necessary for message-driven execution. The message-driven execution naturally follows because once you decompose a computation into a large number of objects, on a given processor, you have many objects. Once you have many objects, there are many possible things you could be doing. Which one to do next? That is driven by availability of a message. That's how the message-driven execution means. That means there is a scheduler sitting there that's picking the next piece, thing from the queue and executing that. Just those two basic features enable things like automatic overlap of communication and computation, the perfect prefetch that I mentioned, and the compositionality that I mentioned. Let's skip past those. In addition, we have migratability because computation is expressed in terms of objects. The programmer is not aware of their location, so the runtime is free to migrate them. We can utilize that for doing proactive fault tolerance or optimizing our fault tolerance protocols. Proactive fault tolerance means, oh, someone tells me this node is about to fail. No problem, I can move things around. The fact that we can actually observe and introspect, the runtime system is figuring out what's going on, allows us to do dynamic load balancing, like I mentioned, allows us to shrink and expand sets of processors we use. That's the part that's relevant to the cloud that I mentioned, and then allows us to do temperature and power aware optimizations as well. So I will just conclude with this slide. Hopefully I convince you it's a sophisticated programming language, a rich adaptive runtime system, and routine used by many application CSE scientists. So believe me, it is coming to a supercomputer or a cluster near you. Because I think the use of this system is expanding. We have a tutorial coming out, we have a book coming out, and so on. This course is available, downloadable from this website. Our license predates open source foundation by a few years. And so, So it is not a standard open source license, but if you have any trouble with the license, tell us. The only thing we don't allow is download and sell the system in some form. So it's freely available for non-selling type of commercial use also. Mostly we say not available, freely available in source code form for non-commercial use or internal use. But if you have any issue with the license, just come talk to me and it should be handled. We have a tutorial coming in ICS this year, and the 11th annual company workshop will be April 15th and 16th in Urbana. I invite you to again at that website. There should be more information about that. I apologize for kind of giving a very broad sales pitch. I would love to give a technical talk at any one of the 10 topics that I heard, and maybe next time I will talk to this audience. That's what I should do. Pick one of the topics and we could talk. But for this time, so we should suffice. Thank you.